Hi, we're about to start our discussion of different types of turbulence. And the first one we're going to do is convective turbulence. So this begins our discussion on convective turbulence. And generally speaking, convective turbulence can be thought of as turbulence that's a result from rising currents of air in the atmosphere. So we're going to start out with a little bit of theory about how heat is transferred through the atmosphere, and then we'll work our way into how to identify that while you fly and how to flight plan for that. So starting out with the theory, we'll do the theory of convection. What exactly is convection? We'll talk about free convection, and then we'll look at thermal characteristics and also the causes of instability. So first, let's look at convection. Well, we know what convective turbulence is. Convective turbulence is turbulence that's felt by an airplane as a result of rising bubbles of air or currents of air. But when an engineer talks about convection, what they're thinking about or what they mean is the transfer of heat through a fluid by the motion of the fluid. Now, whenever they talk about convection, they're thinking three-dimensional. But meteorologists, if you say convection to a meteorologist, their eyes get really big and they start thinking about thunderstorms. So meteorologically, convection is vertical motion. Convection can be either forced or free, dry or moist. Forced convection means that the air is forced to rise first and then becomes unstable after that process. For example, air flowing up a mountain, it's forced to rise up a mountainside, but then at a certain point, maybe the air becomes less dense as it rises, and it will rise by itself and become unstable. Whereas free convection is where the air is initially unstable. Usually this happens with, for example, the air touching the ground, gains energy from the ground, and warms up as a result of that. Convection can also be dry or moist. Dry means that the thermal that's rising does not reach saturation, so it's unsaturated. Moist convection means that as the air rises, the temperature meets the dew point, the air saturates, and it produces a cloud. So as far as the thermodynamics of free convection, we're going to start looking at some numbers of temperature numbers in the atmosphere of rising parcels of air and also the environmental temperature. So we'll start out talking about the dry adiabatic lapse rate. This is the temperature rate at which a parcel of air cools. So as a parcel of air rises through the atmosphere, the temperature decreases because of the expansion of the air. So as a result, the temperature decreases. And that rate is 5.4 degrees Fahrenheit per 1,000 feet or 3 degrees Celsius per 1,000 feet. So in this diagram, you can see a parcel of air starting out at the surface at 10 degrees Celsius. By the time it gets to 1,000 feet, it'll be 7 degrees Celsius. It'll drop off by 3 degrees, and another 3 degrees when it gets up to 2,000 feet, where the parcel temperature will now be 4 degrees Celsius. Remember, this is strictly the parcel temperature and not the temperature of the environment.
On a thermodynamic diagram like this QT log P diagram, the dry adiabatic lapse rate is indicated by a line that starts out down in the lower right-hand corner and moves up to the upper left. If you remember, there are warmer temperatures to the right and colder temperatures to the left. So as you go up through the atmosphere, the temperature gets colder. In other words, it moves to the left. So a dry adiabatic lapse rate, as the air rises, a parcel of air rises along this dashed line. Notice that the temperature does get cooler as you move to the upper atmosphere.
The environmental temperature is basically the temperature profile as measured by a radiosonde as it goes up through the atmosphere. And the temperature profile or the environmental lapse rate varies depending upon a lot of different characteristics. If air is coming down from Canada, then the air will cool, and you'll have a cooler environmental lapse rate in certain layers. Might be warmer as a result of wind moving up from the south. There are a lot of different factors that cause the changes in the environmental lapse rate.
On a thermodynamic diagram such as the QT log P, the environmental lapse rate is shown by a red line. And that red line varies, of course. The temperature varies as you go up through the atmosphere. Generally, temperature decreases, but you may have regions where temperature increases. We call those inversions. The green line on this diagram represents the profile of the moisture in our atmosphere. In other words, that's the dew point.
So we're going to look at how parcels of air rise through the atmosphere, and most times parcels of air get their energy from the surface, the lowest layers of the atmosphere, through conduction. In other words, the air touching the ground warms up as a result of that contact, and this usually happens in the lowest layers of the atmosphere. We're talking the lowest millimeters of the atmosphere. And as a result, you get parcels that are a little bit warmer than the surroundings. Perhaps there are surface discontinuities where the surface is warmer in certain locations than the others. And a good example of that is a black parking lot will heat up a lot more than a grassy area. So you start to get warmer air over those locations and little bubbles of air that start to rise. So as long as the temperature of the parcel of air is warmer than its surroundings, it's less dense, and it'll be buoyant. It'll continue to rise. So this is where you have buoyant parcels of air rising. They're less dense than their more dense surroundings. And as these parcels of air rise, airplanes fly through them, and they experience turbulence. So that is a quick discussion of the thermodynamics of convective turbulence. There'll be another video which talks about the characteristics of thermals next.